Hello, agricultural and food chemistry friends. I'm Mike Appel. I'm a member of the Division of Agricultural and Food Chemistry. It is my honor and pleasure to introduce our speaker today, Dr. H.N. Cheng. He is the ACS past president and a retired scientist from the USDA. The title of Dr. Cheng's talk is The Use of Agro-based Materials to Reduce Plastic Pollution.
Okay, well, thank you so much, Mike, for introducing me, and thank you, Food, for allowing me this opportunity to speak. Today, I'll talk about the use of agro-based materials to reduce plastic pollution. You can see there are some pictures already on the right, what many of us may be familiar with. A lot of pollutants, a lot of plastic waste, either in the land, waste cans or in trash. So now, plastic pollution is really the result of the great success that polymer science had in the past 70 years. So synthetic polymers, mostly from petroleum sources and natural gas, are noted for low cost, versatility, and convenience. And a wide range of synthetic polymers have been made. And most of them, however, are designed for durability. In other words, they're designed to last a long time. And replace most of the other materials used in the past, including many natural materials, natural rubber, leather, bamboo, straw, paper, and wood, and natural fibers like cotton, wool, flax, hemp, and silk. And of course, these materials are coming back as we are more interested in sustainability and renewability. So, however, the synthetic polymers are still the major source of the use of materials. So, they are successful because they are low cost, versatile, and convenient. The problem is that they don't degrade. As a result, and they accumulate. So as more plastic being produced, manufactured, accumulation increases. And the problem is getting worse because we have an increasing problem of plastic waste and microplastics as well. So let's take a look at some of the pictures here of plastic pollution. And these are probably not atypical of what we will see. These are the plastics in the beach. We see a lot of plastic bottles, plastic containers, and all kinds of plastic. Even on the side of the road, people throw their bottles around. If you look at in the water, certainly in the same thing, you see the different plastic containers, different bottles, even in the water. And of course, if you go to landfill, it's even worse, just full of plastics. In fact, I took these pictures from CNN and from April. And in fact, a lot of the plastics we have in the States are given to Southeast Asia. And this is a picture that shows the fishermen in Indonesia. They gather the fish, but then including the fish, they see all kinds of plastic. So the fisherman has to sort out the fish from the plastic. And here's a picture of a beach in Indonesia. And here's the ocean water. And here's the beach. But what are these white materials on the beach? Look at these white materials on the beach. If you zoom in on these white materials, that's what it looks like. It's mostly plastics. So all this white stuff, these are all plastics on the beach. So it's a fairly serious problem that plastics basically plastic waste everywhere. So here's some more information on plastic waste. The world produces around 400 million metric tons of plastic waste each year. Most plastic waste goes to landfill or is shipped to places like Southeast Asia, many of which are already drowning in their own plastic pollution. Every day, 2,000 truckloads of it is being dumped into the ocean, rivers, and lakes. However, only 9% of all plastic produced is currently recycled. A whopping 2 million plastic bags, everybody in the world. Yeah, and so 70% beach litter worldwide is plastics, and approximately 100 million marine animals die each year from plastic waste alone by getting entangled in plastic waste in the ocean, as well as by ingesting it. So this is a serious problem of plastic waste. Now let's look at another problem. This is a problem you cannot see. Plastic waste, at least you can see the plastic. Here, the microplastics, you cannot see them with our naked eye. So here's the optical micrograph of microplastics in water. You can see this different colors. These looks like fibers, threads of something, and there's some particles here, the microplastics. And here's the SEM of microplastics from marine environment. Looks like some kind of entangled threads of fibers. Looks like maybe textile fibers because they are very smooth. They're not natural. Some textile fibers. Now, look at some animals in the ocean. So this was plankton, and this is the green stuff is the microplastics in green. So the zooplankton has ingested some microplastics, and this is a water flea with microplastics in. Look at these white balls. These are probably microbeads, polyethylene microbeads in the guts. So even these animals in the ocean are already infested with microplastics. So here's more information on microplastics. Microplastics, we can safely say now, microplastics are found everywhere. It's found in the oceans, in the water, even in human body. So microplastics is defined generally as things less than 5 millimeters in size, can get into humans in at least 2 ways: by ingestion, for example, seafood, water, food packaging, or inhalation. For example, automobile tires, from the pieces of tires that generated from the tire rubbing on the road, dust and fiber particles from clothing, especially in laundry, carpeting, furniture, paint, and cosmetics. So we actually can absorb these microplastics in the human body. Now, these are the general microplastics by analysis. They consist of polypropylene, the major part, polyethylene, PET, polyethylene terephthalate, PMMA, polymethyl methacrylate, polystyrene, and others. So these are the common plastics being used anyway. So the common sources of microplastics are degradation, larger polymer items, for example, tires, synthetic textiles, for example, polyester, nylon, plastic bottles, shopping bags, products, and they usually use small plastic beads like polyethylene, in order to do better cleaning on the skin. And the road dust and laundry, these are top sources of microplastics. In a recent report, actually interesting, very recent, March 2024, the Italian scientists actually found nanoplastics in the human arteries. And even more so, that they have shown that the presence of these nanoplastics can be tied to a higher risk of heart disease. This is an article published in New England Journal of Medicine, so a very reputable journal. So you can see that this is a serious problem. Both plastic pollution and microplastics are a problem. And to show the gravity of the problem, here's a global accumulation of plastics. Plastics really gets used in the 1950s, starting out in the 1950s, and it increases, almost explosive increase. And this shows accumulation because once you make a plastic, usually you don't destroy it, you just accumulate so that you have, right now we are talking about 9 to 10 billion metric tons of these plastics being accumulated. And here's another graph that shows some forecast. So here, the same thing, this annual production, 1950 to 2020, projecting to 2050. So you can see that between 2000 and 2020, in the 20 years, more than half of the plastics ever produced have been made. 56% is, look at the area, 56% have been made in the last 20 years alone. If you project into the next 30 years, look at the area under the curve, even more so in the future. In fact, the United Nations expect this production to triple by 2050, according to the Chemical Engineering News, an April 15th issue this year. So this problem is not going away. This plastic problem is going to increase. It's going to get worse in the future. So what are the problems of plastic waste and microplastics? Perhaps it's obvious, but let me show you, just to summarize here, the environmental impact, because the plastics are slowly degrading, they accumulate in landfills and oceans. Entanglement ingestion by wildlife and by humans as well. Microplastics gets consumed by marine life, accumulating the food chain. So that's environmental impact. The human health concerns is that microplastics has been found in drinking water, seafood, and sewage. So potential health risks of ingesting microplastics are being studied and already just noted with heart disease, concern about potential toxicity and long-term effects has increased. For the economic implications, plastic pollution negatively impacts tourism. Certainly, tourists wouldn't like to see all this plastic trash, on the road, on the side of the road, or in the beach. For fishing industry and coastal businesses, and clean up waste management costs are substantial, and there's no easy solution to plastic pollution problem. So that's really a big concern. Now, people have been trying to address the problem of plastic waste and microplastics. And here, just a summary, one major area is policy change. For example, a major policy change is to regulate the amount of plastics that can be produced. And this has to be a global effort because there are lots of countries in the world. And the United Nations have been trying to do this. They have a program, it's the United Nations environmental program, and they've been meeting. In fact, they met in Ottawa in April of this year, but it didn't come to any agreement. People argue over different countries, argue over different things. The whole idea is to reduce the plastics being produced globally. Everyone needs to agree, in order to control the amount of plastics being produced. But there's a policy changes. There are others relating to, of course, the safety and the disposal and the management of plastics. So it's an important part, and government has to get in. Of course, scientific innovation and public awareness. We need to bring this problem to the public so people are more educated about this problem, and they will modify their behaviors accordingly. So they don't, you can use less waste, less plastic, reduce the waste, and reduce the single-use plastics, for example. So they can use behavior modification. So it really needs collaboration between government, industries, the scientists, and consumers. Now, we are scientists, of course. So what are the things we as scientists can do? We can do a number of things here. And for example, we can develop biodegradable and compostable plastics that can break down more easily in the environment and reducing their persistence and impact. So these materials are designed to be broken down natural processes such as hydrolysis and microbial action. So to use degradable, compostable plastics, or we can use plastic alternatives. So we can, for example, we can use agro-based bioplastics, and they're derived from the renewable sources. And because they are renewable, and the agro-based material tends to be less toxic or non-toxic, and they are also to the plastic pollution. So that would be probably a longer-term solution because if we replace most of plastics with agro-based materials, we can still have the benefit of the plastics, but we will minimize the plastic pollution. And I'll talk more about this. And the plastic recycling, it is a lot of work ongoing on plastic recycling, different ways to recycle. Yeah, and so this is a huge area. The one problem with plastic recycling is that you recycle, but it's still there. you're converting one plastic to another plastic, or you're upcycling to different application. But plastics, for the most part, it does not disappear. And so you're just converting one problem into another problem. But it doesn't mean we shouldn't do it. We should do it in order to reduce the amount of plastic being used. But it is one of the approaches, certainly. The microplastic monitoring and removal. So that is something people have been working on. It's difficult because microplastics are so small. People have been talking about use of specialized filters, nets, and sensors to detect and collect microplastics particles. Certainly more research is needed. Now, more approaches, ocean cleanup technologies. And there's a wonderful initiative called Ocean Cleanup Project, and they use these floating barriers and vessels to sort of capture and group all these plastics in the oceans, group them together and remove them from the ocean in order to clean up the ocean. It's a wonderful initiative. And another approach is the plastic degrading methodologies. A lot of work ongoing. People use enzymes and microbial organisms in order to digest or break down plastics like PET, and others. Yeah, and so this is certainly an excellent approach and can help in the overall situation. Eco-friendly packaging. Packaging by far is the largest polluter, the plastic polluter. They contribute the most to plastic pollution. So R&D efforts are ongoing to develop sustainable packaging materials, including research into reusable packaging, paper-based alternatives, and packaging made from agro-based materials. And there is enhanced waste management, another approach, and in order to reduce plastic litter from entering the environment, including the development of more efficient landfill incineration technologies. And there are two approaches relating to the analysis. So the circular economy is to analyze where the product is going and how they can be recycled and the use can be reduced. And especially for single-use plastics, and life cycle analysis, especially very good. Where is this plastic comes from, where is it going, where eventually can be disposed of or can be recycled. So you do the analysis ahead of time in order to have in the future for better management, material choice, and management strategies. And of course, we need to, scientists can contribute towards education awareness of the public, and so that we can work together to raise public awareness about the issue and promote responsible plastic use. And of course, we can work together, scientists can work together with the policymakers, the government, policymakers, regulatory bodies about environmental consequences of plastic pollution using evidence-based policies, can reduce plastic production and encourage responsible consumption and disposal. So here is what most people consider the 4 R's of plastic management is reduce, reuse, recycle, and the 4th R, people have different views on how the 4th R should be. Some people say we should recover, R should be recover. Only some people say we should reject and refuse, which means we just don't use plastic at all. Or I like another alternative for the 4th R is renew. In other words, use renewable materials for the 4th R. And I like this 4th one. And I think this would be a promising research approach. Now, I'm affiliated with USDA, and the USDA, we very much believe that the agro-based materials can contribute a lot towards the reduction of plastic waste, because agro-based materials are biodegradable and they are non-toxic. And it also helps by using more agro-based materials, helps the farmers as well. So this approach, and showing in the slide, incorporates 3 different technologies. There's a green chemistry, there's a polymer technology, there's agro-based materials. So we combine the 3 together, we then can build a platform for new materials, agro-based materials, as a possible replacement or partial replacement of plastic. And from using this chemistry, green polymer chemistry, we can synthesize new polymers. We can do polymer reactions to improve the polymers. We can use blends and composite again to improve the properties. We can formulate the products in order to produce new and better processes and greener. And of course, this is also consistent with ACS thrust. ACS has a Green Chemistry Institute and has been championing the idea of green chemistry for quite a few years. And ACS has certainly divisions relating to polymer chemistry. I think there's a poly, PMC, colloid, these materials, and certainly the division of ag and food chemistry has been a major contributor towards agro-based materials, and so is agro division. So I think it's also this effort will be consistent with what ACS members can help. So what I will do is I will show you some examples involving the work that I've been doing together with my collaborators at USDA in the past several years, just a review of some of the work, just to highlight some of the possibilities. So this includes, the goal is to avoid microplastics in one case, avoid non-degradable resins in the second case, reduce plastic packaging, and then the third case, reduce the polymer waste. So those are the 4 examples I will show. So the first example is greener wood adhesives. So we know that wood adhesives considered a huge business. The 2016 worldwide revenue was 15 billion. The most of the resins for wood adhesives are the formaldehyde resins, the urea formaldehyde, phenol formaldehyde, melamine formaldehyde, the mixed formaldehyde resins, and that constitutes 70% of the materials. And the second largest is diisocyanates, the urethanes. Now we know that formaldehyde resins are not easily degradable. Therefore, formaldehyde is toxic and also potential carcinogen. Therefore, they accumulate in the landfills after use. So there's increasing interest because of the interest in minimizing petroleum-based materials. There's increasing interest in using natural bio-based materials. The greatest interest so far is in soy proteins. Right now, it accounts for about 3% of the revenue for the wood adhesives. And already we have commercial products involving, I think there are at least 2 companies that produce commercial product involving soy proteins as wood adhesives. Now, the wood adhesives, in order for any new product, including soy proteins, to be competitive, we need to consider the cost of the product and also consider the performance, including the dry adhesive strength and the wet water resistance. So we need to consider both cost and the performance. Now, I'm affiliated with the Southern Regional Research Center at USDA. We are based in New Orleans, and it's in the South, American South, and the South in America is big on cotton. So we look upon the cotton-derived products as a possible good resource for agro-based materials. So we study cottonseed protein as an alternative protein for wood adhesive applications, comparing ourselves, for example, to the compare cottonseed protein is to make a blend. For example, this is 100% cottonseed protein. No, I'm sorry, this is 100% soy protein, 0% cottonseed protein. And here is 100% cottonseed protein. So you can see already cottonseed protein relative to soy protein is performing a better adhesive strength. So the performance-wise, we are already seeing advantage using cottonseed protein. If you make a blend, then you just have a continuous performance between the 2 things. The 2 proteins are compatible. So that's one approach, is to blend. The second approach we found out, in order to lower the cost of cottonseed protein even further, is blending an inexpensive polysaccharide. For example, cellulose, just the regular, the cheap cellulose, say from pulp and other things, any material. We can do a mixture, cottonseed protein and cellulose mixture. Cottonseed protein, 100% cottonseed protein, has this dry adhesive strength and this hot water resist, these 2 values. If you're blending the cellulose up to 75%, you can see the values don't change that much from the original value, which means that cellulose is found as a filler up to 75%, keeping adhesive properties unchanged and lowering the cost. So here's an approach, because the key thing here is the performance over cost. You can either improve the performance or you can reduce the cost. And here's an approach where we can reduce the cost, keeping the performance the same using cellulose. However, if you use nanocellulose, we can actually improve the performance as well. So here are the data for two types of cotton nanocellulose, cellulose nanofiber and cellulose nanocrystals. So for nanofiber, even at 2% level, we reach 2% level, we can increase the performance adhesive strength by 22%, even at 2% level for fiber. Whereas for the nanocrystals, you need 10% in order to get 16% advantage. The reason is because the fiber is more effective than crystals, is because the nanofibers have much longer aspect ratio than the nanocrystals, so they are more effective. So the bottom line is that nanocellulose can actually enhance adhesive performance. So here's a case where we can increase the performance as well. Now we have shown, to our surprise perhaps, that we can improve the performance even more, especially by using anionic polymer. Sort of improve the performance, but the best additives are the anionic polysaccharides. The carboxymethyl cellulose increase the dry strength by 56% and the wet strength by 34%, a huge number, huge improvement. The low methoxypectin also improves it fairly well, 39% and 28% respectively for dry and wet. And alginate somewhat less, but it also improves it. So basically, we see significant enhancement observed for CMC and pectin. Now, what's interesting is that this only works for cottonseed protein. If you use soy protein, it shows no enhancement. So this effect is only good for cottonseed protein. So the question is why? Only works for cottonseed protein. Now, we know the adhesion of adhesives on wood depends on two effects: interfacial coupling between the protein and the wood surface, and the formation of cross-linked protein structures during heat bonding. Now, cottonseed protein contains a lot more arginine than soy protein. And arginine contains vanadium ion, the cation, as a pKa of 12.5, which means it's cationic up to pH 12. And the cationic arginine helps to couple the protein to the wood. The wood in most cases are anionic. Most natural materials, they tend to oxidize. The surface tends to be anionic because of oxidation. So having cation helps with binding the anionic wood. And by adding additional carboxylic acid like anionic polysaccharide, and phosphoric acid also works, interacts with cationic cottonseed protein in order to give it a stronger adhesion. And indeed, FTIR shows that there are specific interactions between cottonseed protein and the carboxylic acid and the acids. Now, of course, in addition, the Maillard reaction can happen between protein polysaccharides, and of course, it will enhance the strength of the materials even more. So this shows that indeed we can find replacements for formaldehyde resins using cottonseed protein. It's environmental better and also reduce the problem of plastics. The second example is for food packaging. As mentioned earlier, this is the biggest contributor towards plastic pollution. And we know that plastic is doing a great job protecting food from contaminant and spoilage, especially polyethylene and saran, which is polyethylene chloride with some acrylates and copolymer acrylates. So they do a good job, but then the packaging after use. Agro-based materials are increasingly being used because it's biodegradable, non-toxin, sustainable. And a lot of research work is being done, including myself and my collaborators at USDA. And so you can see here, here's many of the things we have tried: cellulose esters, cellulose ethers, especially for food coatings and packaging, water-soluble food coating and packaging. And we have been using agricultural byproduct waste to reduce costs. We have using blends and blend films to formulate new polymer films and also improve the properties. And we have also used biocomposites to reduce costs and plastic use, and the use of nanomaterials to improve the properties. I just show you one slide to show our work on nano composites. And we know that the composites typically contains at least two components. There is a discrete phase, sometimes called the filler or the functional filler. And then there is also the continuous phase, which is sometimes called the matrix. And so in this case, what's frequently done is to take a synthetic polymer or a biopolymer synthetic polymer as a continuous phase and add agro-based material as a filler. So here are some three examples. Here is polyvinyl alcohol and low-density polyethylene and polypropylene. These are all synthetic polymers, and we can add agro-based fillers like edible beans, cotton gin trash, nutshell, cotton burr, and hull, and other materials. And we have published a lot of this work, and this is an example. So here is polyvinyl alcohol with gin trash SEM picture. Both of them are hydrophilic, so you can see that they adhere fairly well. These materials, the filler and the polymer matrix. And this is a low-density polyethylene with beans. Now, the low-density polyethylene is not hydrophilic. Beans are. So you can see that the materials don't adhere as well, but we can make a blend accordingly. So the key thing here is that as long as the performance holds up, for the application in question, holds up, we can use the fillers to reduce the cost, and therefore also reduce the plastic use. So we can do filler as much as 40% in order to reduce the plastic. So we still have the benefit of the plastic, but reduce the use by using bio-based, agro-based fillers. Now, a third example is the avoidance of microplastics. So a cotton gin mold is a byproduct, a waste product cotton ginning process. It is very cheap, but can become a source of microplastics because these are discarded. You can, once it's not being used, so you discard it and it gets in the water stream, gets in the air, so it can be a source of microplastics. It contains small broken immature seeds with fibers. And the cellulose content is about 60%. So instead of throwing them away and becoming potential microplastics, we have, my collaborators and I have made nanocellulose from them. So both the nanofibers and nanocrystals. And here's an application how we can use it for value. So this is paper. Paper is a huge, very, very convenient product, but the most valuable property of paper is the strength of paper. Whether it's a writing paper or newsprint for newspapers or for boxes for packaging, the strength of paper is the most valuable property. And this paper by itself, the tensile strength 9.7. If you just add the nanocellulose to the paper, it hardly changes. However, if I were to add 10% cottonseed protein to the paper, you see it doubled. You have doubled the tensile strength of paper, so giving value to the paper. And if you add on top of cottonseed protein, you add the nanocellulose crystals, the crystals and the fibers, you can see you add additional boost to the tensile strength, indicating indeed that both the cottonseed protein and the nanocellulose fiber and crystals from the cotton gin molds can add value to this material. So here is a case where we can convert potential microplastics into value-added product. The fourth example is a polyurethane from carbohydrates. We know polyurethane is a huge business. It's many different commercial uses. They're usually made from petroleum-based building blocks, diodes, polyols, polyether diodes, and polyester diodes. However, polyurethanes are not easily biodegradable and can easily pile up in landfills. So we use carbohydrates as building blocks that can be degraded. So my collaborators and I have done this for several carbohydrates like sucrose, sorbitol, lactose, cyclodextrin, maltodextrin, and xylan. And on top of that, in order to improve the property, we borrowed a page from polymer chemistry. This is the semi-interpenetrating polymer network concept. So we added the second polymer to this polyurethane in order to improve its properties. And I'll show you some examples of that. So here is the reaction, a very simple reaction, almost green reaction. We just take the TDI, and just heat, and then you can generate this polymer. And we did it with both conventional heat as well as microwave. And so here's conventional heat, 20 minutes, microwave, actually 5 minutes, you get the same yield. So here is a way where, again, a greener process. Using microwave, you can save energy or save time in terms of the reaction, and you get the same product. Now, the problem with sucrose polyurethanes is that it has been published before, by convention, it has been published before. There's not much interest because they are very brittle. But however, our work on fast microwave encourage us to improve its properties. And the concept here is a semi-penetrate network. So basically, you add a second polymer in order to produce a semi-penetrate network, and therefore borrow some of the properties of into the polyurethane. So proof of concept, we have done this for polycaprolactone as well as soybean oil as a second polymer. So the reaction is fairly simple. It's fairly straightforward. The same thing as before. We take TDI together with the sucrose, and we just add the polycaprolactone on top of it. So they are polymerized together. As the TDI and the sucrose form a polymer, it encapsulates or it just entangles the polycaprolactone as a second polymer, and you form basically an intimate blend. And so this will be 2 levels of TDI, 2 levels of polycaprolactone. We're done with conventional heat and microwave. Conventional heat takes 20 minutes, microwave 5 minutes. So again, saving time and energy using microwave. And the yield are very, very similar. If anything, microwave is slightly higher because you heat so fast, you can force them to get together. There's no time for phase separation. So again, saving time, energy, and get the same product. And just to prove that you get benefit from it, so this will be sucrose, TDI, and polycaprolactone as soybean oil at 0.50% level for the second polymer. Sucrose plus TDI, you can see this will be mechanical strength, yield modulus, tensile strength, elongation, break. Sucrose plus TDI is very brittle, you don't get any value. If you add soybean oil, you already get some values. You're not very high value, but you get some values. If you add polycaprolactone, look at that. You get very nice values. And this is, if you compare with the polycaprolactone by itself, you get very similar values, indicating that now polycaprolactone is fairly expensive, but sucrose is very cheap. And if you add this polyurethane to polycaprolactone, you can decrease the cost. So basically, you can get a lower, greener, biodegradable polyurethane. So this was published a few years back. So now I've just given you 4 examples, and if you're interested in more of my research, you can check my website and for the full range of work I've done. And I was fortunate to be elected as part of the ACS presidential succession, and I served there, let's say 2020, 2022. And one of my initiatives was sustainable green chemistry. And the purpose is to promote and publicize sustainability in the chemistry community, fostering innovation, collaboration, promote sustainable manufacturing, encouraging sustainability across the globe. I've organized lots of symposia as a result. and talked to ACS on campus, given many talks, and written many articles, and even edited books in 2020, also 2023, 2 volumes. So this is the latest 2 volumes I edited in 2023, December, late last year, and the Sustainable Green Polymer Chemistry in Polymer, Green Chemistry in Polymer Research, Volume 1, Biocatalysis, Bio-based Materials, Volume 2, Sustainable Polymers and Applications, and together with Richard Gross at RPI. So the final thoughts is that this talk highlights a serious problem, plastic waste and microplastics, that needs immediate attention. So the agro-based materials constitute a good R&D approach to mitigate this problem. This can be done in combination with the use of green polymer chemistry and efforts to reduce plastic waste, non-degradable products, and microplastics. Of course, we need continued investment in research together with implementation and combination technological solutions. Now, at a personal level, we can all help minimize plastic trash by recycling plastic items and avoid littering. So as citizens, we can all help out in this effort. So working together, we can mitigate this problem and help to conserve the earth. And here, just a graphic. So if we all do that, so this will be, again, the plastic trash, and we can hopefully convert it into better and more ecologically safe, greener world. And I need to acknowledge many people and collaborators. And at USDA, we have my friends, Atana Biswas, Mike Appel, who is the moderator, Zongki He, Mike Dowd, Jacobs Jordan, Mike Eason, and Thomas Clausen, my research leader. And we also collaborated with the Brazilians, Rosalind Furtado and Colosio Alves. And I've also collaborated with other colleagues in universities and other organizations. So this ends my talk. I'll be glad to answer questions.
Well, thank you very much, HN. What a great talk, very engaging, and it really gets to the heart of one of our current main issues. For those who don't know me, I'm Mike Morello. I've been a long-time member of the Ag and Food Chemistry Division, and I'd like to coordinate any of your questions with HN. So we have one question in the chat from Lin Shu Lu, who says, great presentation. Bio-based materials are tested as alternatives to thermoplastics. Is there any potential negativeness needed to consider now?
Okay, that is of course a very good question. Thank you. Now I would say currently the major challenge of adopting bio-based material, agro-based materials is the cost. So because in the synthetic polymers has been around for 70 years, the most common polymers, the process of making it has been improved for so long that the cost can be as low as it can be. And so if you want to take a material for drop-in substitute, we need to compare the cost of the starting material, and there is basically the economy of scale. Now, that's why a lot of emphasis my collaborators and I have been doing is to take agricultural waste material and byproducts. So these are materials that are considered less value and therefore cheaper. And therefore, by using them, we can then make them more competitive with synthetic materials. And that's a major part. And of course, there's also a performance issue because, again, plastics has been around for 70 years. People have already, through different iterations, have improved the properties. And that we are trying to do as well. For example, by using blending, by using formulation in order to match the current process. That's for existing applications. Now, if we are looking for new applications, then of course, we are under less constraint.
Okay. Thanks, HN. We have another question based on, would the use of biopolymers reduce the appearance of PFAS, the PFAS issue with packaging?
Yeah, I think of course, in our agro-based materials, we don't use PFAS, and PFAS is less of an issue. People do use PFAS and for like, for example, for animal for pet food, for example, applications. Yeah, but it depends on the application. So for the most part, it's not necessary that we can avoid it.
Okay, another question we have, it relates to what type of testing would you recommend for biodegradation?
I think, yeah, I'm not a microbiologist, yeah, but and I know in the audience there are people that probably can answer that question better than I do. But there are some standard methods people do use by mixing the materials together and use a concoction of microorganisms, trying to see how much degradation it is, and this is. This can be done. If I were to do it, I need collaboration. Yeah, since I think for me to publish a paper, I would need someone, a microbiologist who is someone versatile, who is more conversant on microbiology, so that the results are carries more authority.
Okay, just for myself then, HN, I think I'll ask the question of, as we're looking at agro-based bioplastics, if we're using the similar polymerization techniques that have been used for years, what makes bioplastics less detrimental to the environment or more amenable to recycling than traditional petroleum-based plastic?
Yes, I think that is where creativity, that's a very good question. That's where creativity comes in. We can borrow the idea of polymerization to bio-based materials. One good example I showed you is the polyurethane. We are still doing the polyurethane reaction, but we are, instead of taking polyores from petroleum source, which is not biodegradable, I'm taking, say, sucrose or lactose. These are disaccharides, and disaccharides can be easily cleaved between the two sugars. You can cleave them and therefore make the polysaccharide degradable. Whereas if you start with a polyore, whether polyethylene glycol or diglycol or poly-THF, and they are not as degradable. And so that's triglycerides. A lot of people work on that. And then you can still use, say, vinyl polymerization, but then you graft it onto the triglycerides so that the triglyceride itself can be degraded, and then you build up the polymer through that means. And we have also, in collaborating with my friends at USDA, we have quite a few other reactions involving triglycerides using polymer chemistry, like the yin reaction, where you can actually generate a polymer as well. So there are many ways where, through creativity, by borrowing concepts, established concepts from polymer chemistry, but applying them to the agro-based polymer, because agro-based polymers are inherently more biodegradable. So now you have a material that has a benefit of both worlds. You have some of the structures, functions of synthetic polymer, but because your platform is biodegradable, so material tends to be more biodegradable. So that's where you sort of borrow from different technologies in order to produce a new methodology or technology.
Okay, thanks. We have a couple more questions. There's a lot of potential for ag-based plastics. What would you suggest to do with the existing waste plastic until we completely switch to bio-based, biodegradable plastic?
Okay, so there's a fair amount of work being done on recycling of plastics. And there are some very clever ideas, clever ways of doing it. Actually, I actually have 2 slides in my backup slide. And you want me to show them? I can show them quickly if you want to do that, or I just answer.
If you can show real quick, I think we want to end on time, but go ahead, please.
Oh, okay, all right. Let me just show very quickly. Okay. Yeah, so here are some common recycling methods. This is mechanical recycling, involves sorting, cleaning, processing plastic waste by melting, extrusion. There's chemical recycling by breaking down the plastic into original monomers and other useful chemicals using depolymerization, pyrolysis, and gasification. There's a feedstock recycling, converting plastic waste into fuels or chemical feedstock. There's a plastic to plastic recycling. The plastic recycled into the same or similar type of plastic products. For example, PET bottles can be recycled to other PET bottles, and upcycling, take plastic waste to create products higher value or quality than the original materials, like plastics transformed into fashion items or artwork by mixing with other materials such as wood, fiber, or glass. The composite material can be used for construction, furniture, and other products. Like, for example, polyolefins can be recycled with sawdust in order to produce this furniture. Yeah, and the 3D printing filaments, certain plastic can be recycled in the 3D printing filaments. The plastic lumber, yeah, this is the same concept. Plastic lumber, like high-density polyethylene, can be recycled in durable plastic lumber. Outdoor applications like decks and fans, or eco-bricks involves filling plastic bottles with tightly packed plastic waste. And these bricks can be used for construction in some regions, reduce environmental impact for plastic waste. So you can see here that it's limited only by the creativity of the people involved, that we can take plastic waste, either upcycle it or downcycle or recycle. So there is opportunity for an entrepreneurial person to find opportunities for this plastic waste.
Okay, and we do have another question, and this relates to the use of green plastic in food application, food packaging materials. Oxygen penetration is an important issue. When you're looking at the green plastics, do you test for the pore sizes for the different polymers to make sure that to look for oxygen and different vapor penetration?
Yes, in fact, it's fairly typical for when we do the packaging. Very typical for us to measure the permeability of moisture and air of the plastic, because that's certainly a major consideration when you have a packaging. And so by measuring permeation, and sometimes we use, for packaging especially, we use not a single layer film, sometimes we use bilayer films in order to improve the properties. Yeah, and it's very important. And there is also a possibility, and I think we have a paper on that collaborative paper, where you can actually add additional items into the film. For example, add nanoparticles of palladium, which absorbs the oxygen. And so that you can reduce the oxygen level after packaging. The palladium can actually absorb the oxygen even more, residual oxygen, in order to minimize the oxygen. Again, it's only limited by the creativity. So we have many ways where we can design the packaging.
Okay, no, very good. I'll ask Mike Appel if you have, Mike, do you have any further comments or questions?
Yes, I do have one question. HN, there's a recent popular meme that oil is made from the remains of dinosaurs and plastic is made from oil. So plastic dinosaur toys are made from real dinosaurs. Is replacing traditional plastics with biomaterials more than just a way to speed up the reusability of resources, or is there another benefit?
Yeah, well, I think that is, of course, interesting concept. I think the problem with dinosaurs is fascinating. Only trouble is there are only limited number of dinosaur bones available. And so that horse, maybe can be used as collector's items, but dinosaur bones are so valuable. There's increasing interest by archaeologists, that dinosaur bones can, are probably too valuable for the applications. I know in the old days, people even use dinosaur bones for medicine. Yeah, and because they consider these large bones curiosity items. So, and that's in the old days. But today, okay, if we have dinosaur bones, they probably should belong to a museum. And people are, now, of course, dinosaur bones are probably too old. And now with technology, the paleo archaeology, people can even sample the DNA of Neanderthal and Denisovian humans, so that 300,000-year-old bones you can still obtain DNA from. And so maybe people, scientists are interested in old things, and so that may be something to consider.
Okay. Well, I think we'd like to thank HN for a great presentation. We really appreciate him kicking off our Agricultural and Food Chemistry Division webinar series. We hope to have more of these in the near future. And I want to thank everyone for attending. We appreciate your participation, and thanks to everyone. We appreciate your time and attention.